Where's the Balmer series go?
We'll go back to it.
It's cool, Kim, yeah.
Okay, so,
I can
So
do
if
this.
we're gonna take
I know. So as we get into the last chapters 29 and 30, so we're gonna kind of just lump them all together. So, to understand how we're gonna be dealing with like isotopes and nuclear interactions, I need to have a quick refresher on isotopes and symbols, okay? So, you have mass numbers and you have atomic numbers. What's the difference between the two? Will Stanley?
Yeah. The atomic number is correspondent to the number of protons in the atom.
Beautiful. Spot on. And where are you going to find that number?
Bottom left
Of the, no, on the periodic table.
on the periodic table,
Is it the decimal or the whole number?
the whole number,
Okay. On the chemical symbol, where are you going to find it?
bottom left.
Bottom left. Okay? So, and this is, it's simple, but it's important. What's the only thing that determines the type of atom an element is? There's only one thing and one thing only. Number of protons. Number of neutrons doesn't matter, the number of electrons doesn't matter, you can gain, lose electrons, you can alter the number of neutrons, doesn't matter. It is strictly the number of protons that determines the type of atom. So if you look at, like, for example, helium, okay? So if you have this, and we'll talk about the difference in this in just a second. So if you see 4, 2, so the 4 up there is what, Will Stanley? The mass number or the atomic number?
Mass number.
That's the mass number. And the mass number represents the total number of what, Will?
Particles
Where?
in the nucleus,
And what are the two types of particles in the nucleus?
protons and neutrons.
Okay, so the mass number is the total number of protons and neutrons. Can that ever be a decimal? No, I can't have like half of a proton or half of a neutron, okay? So your mass number is always going to be the bigger number. Neutrons, they're there, and we'll talk more about neutrons later. Neutrons basically act to stabilize the nucleus. And the bigger the nucleus gets, the more neutrons that you need to stabilize it. But unfortunately, the bigger the nucleus gets, it's kind of like building a tower out of jello. It becomes more and more unstable, and then you can split it, and that's how you get, like, fusion reactions going. Or fission reactions. Now, you get into this, carbon-13. So this is what was on that last test, right? So you have carbon-13. So if you have carbon-13, you have 6 protons, and you have how many neutrons? 7. Okay? So you got this. Now, as long as there's nothing written in the top right-hand corner, what do you assume about the number of electrons and the number of protons?
Even.
They're even, okay? So if there's nothing written in the top right corner, you assume that the atom is neutral. So if you look at what Rutherford did alpha particles. And the reason that they called them alpha particles is they literally did not know what they were, okay? He goes, hey, I don't know what they are. Hey, I don't know, call them alpha particles. Well, it turned out that they were a helium nuclei, but it had stripped off the 2 electrons, okay? So basically, it was just the nucleus of a helium atom. So there was any number of reasons that they didn't know what to call this. Number one, they hadn't even discovered helium yet at that time when the Rutherford was doing this. It was like, I don't know what it is. It's some positively charged particle. And he knew that because they had a radioactive source. It was like thorium-238 or something. I don't remember the exact. But it would shoot out these particles. And again, he could not see the particles. But what he did is that he put an electric field on either side of it, and he shot those particles through. And those alpha particles were deflected towards the negative and away from the positive. He goes, oh, right, the only way that can work if these particles are coming up in a path like this, which means that they have to have a positive charge. And again, this is like from that book yesterday. You could not see them. So what they would do is they would have a phosphorescent screen in a dark room. And they would see little flashes of light. So old school. If this was the electric field, negative up on top, positive down below, and you're shooting this positively charged particle through it. So it's going to deflect this way. It's a positive charge. How would you set up the magnetic field to make it go straight? Oh, so you got a positively charged particle going this way, right?
Out of the page, out of the page.
Out of the page?
Wait,
Yes.
into the,
into.
yeah, into.
What?
It's a positive particle.
Into.
But you're going.
Yeah, no.
That's your force is going down, your force going up.
Yeah.
Your
No,
force going up.
the electric field has a force that's going up. Wait, do we want to counteract it?
I want to counteract
Yeah, so you want the force going down?
I want, so which direction do I want the force?
Connor, you're gaslighting people against me.
Which direction do I want the force in the magnetic field to act?
Down.
Downward, right? I want the force in the magnetic field to push it down to balance out the electric field. So the particle is going this way, true? I want the force to act downward. So which direction does the magnetic field act? Out of the page. So you would have dots or X's.
Dots.
You would have dots.
I like those.
Okay? So the electric field would be going like in this plane, and the magnetic field would be going in this plane. And you could set the two values equal to each other. So that allows you to basically sort through the particles and go, okay, hey, only certain particles with a certain velocity and a certain charge are going to make it through and go straight through. So then he put the gold foil there. So then he knew, oh, hey, I'm shooting gold foil. Now, there's a couple of things we're going to go old school. We're going to resurrect ooey. So imagine here is this alpha particle. And here's this big, massive gold nucleus. So this is positively charged. As it's moving, what type of energy does it have? Kinetic. Now, if it hits just right, as it gets closer and closer and closer, this is positively charged. The massive gold nucleus is also positively charged. So as it goes, is it going to feel repulsion or attraction? Repulsion. So as it goes, is it going to speed up or slow down? Slow down. So if you know how much energy that it has, if you know how much kinetic energy it has, you could set that equal to the amount of ooey that it's going to have when it stops. So it would be like compressing the spring. So how do you calculate ooey?
Good question.
That is a good question.
Give me a couple.
Perhaps a K?
No, I don't know.
Perhaps a Q?
Wait, actually, what are we talking about here, Bert?
Perhaps
Q2 over
another
R.
Q?
Over D.
Overall.
R or D or whatever you call it.
Oh. Over D or D squared?
D.
Pick one.
Okay. Old school. What units are K? Something.
It's like, isn't it like 8.5?
I just want the units.
Units.
Newton meter squared over
Newtons, you said it's, what was it, Sydney?
Newton meter squared over Coulomb squared.
Over Coulomb squared. Ah, because on the top I've got what?
The units for K.
Coulomb squared. Now, if I divide by meters, what do I have left?
Meters.
I get Newton meters, otherwise known as, which is what OE is measured in. Now, if I divide by d squared,
That's force.
that's force, okay? So KQ1, Q2 over D is OE. If you divide by d squared, you get force. Big difference between the two. So, this basically is what Rutherford was able to do. He calculated how much kinetic energy that it had. He knew the mass, he knew the velocity, because it had to be selected for a particular velocity coming out. So he knew the kinetic energy side, which means he also knew the OE side. So then he could get what was known as the point of closest approach. How close did those particles get before shooting backwards? So if he knew that, and he knew the value of K, and he knew the charge on the alpha particle, he could find the missing charge that was on the target. Okay? Or if he knew what the charges were, he could calculate that point of closest approach. So this is nothing more than like saying, hey, I've got a cart with a spring. It's going to roll in. I'm going to store that as potential energy, and then it's going to bounce back. But on kind of a scale, to put this in perspective. So imagine that I've got this tennis ball here, and I'm going to take Hank the bowling ball, and I'm going to put Hank in the back of the room. Then I'm going to turn out the lights, so it's dark. And then I'm going to start blindly throwing the tennis ball towards the back of the room. Okay? Most of the time, what's going to happen? It's going to miss, because most of the back of the room is empty space. Now, even if it hits the bowling ball, odds are, what's it going to do? It's just going to bounce off, okay? So every once in a great while, what's going to happen? I'm going to hit it just in the middle of that bowling ball, and it's going to bounce back. Pretty long odds, though. That's basically what happened when Rutherford did his work with the alpha particles in the gold foil. Most of the time, the particles went straight through, even though the gold appeared solid, like you couldn't see through it. And this is where the atomic world got so weird, is they sat there and said, you know, most of the time, this is just empty space. Even though it doesn't look like empty space, it doesn't feel like empty space, it feels incredibly solid. But on an atomic level, it's mostly empty space. But you're going, this doesn't make any sense. We can't see through it. It's like, so this became part of the challenge. Like, okay, I got this table, pretty solid, can't see through it. I've got this glass, pretty solid. Still made of, everything's made up of protons, electrons, and neutrons. So the question being is, why can I look through this glass and see a certain K-State shirt, yay for K-State, but if I hold up this, I can't. And it's made up of electrons, protons, and neutrons. Photons. So the question being is that for me to see that purple K-State shirt, what has to happen? What do the photons have to do? Pass through. They don't interact. So the question being is that why do the photons go through the glass and not interact? Well, why do the photons interact with this and bounce off?
I don't really ask
Frequency.
It has to do with basically the structure of this. So basically, anything that happens is clear. It's because there's nothing in there for the photons to interact with, and they just pass through everything. Whereas if it's like that purple sweatshirt, it actually absorbs every color but purple, and the purple is what gets reflected off. Okay, now, Balmer series. On the test, I'm never going to expect you to do Balmer series calculations.
Perfect.
I'm just introducing it, so it's one of the classic kind of physics, quantum things that you need to know. So this is just for background information. So the Balmer series was the greatest probably example of trial and error and guess and check that ever existed in all of science.
Oh.
No, it's true. No, it did. It was just, or my multiple choice questions, whatever.
Yeah.
So here's literally how this happened. They had to explain the spectral lines of hydrogen, okay? And at the time, they had no idea of quantum states, anything. So literally, this is what they did. They said, okay, we're gonna have two values. We're gonna have m's and we're gonna have n's, okay? Those are their integers, their whole numbers, m's and n's. So m can be anything from 1, 2, 3, 4. They're all whole numbers. That's a good thing. They're all whole numbers. So they viewed like if m equals 1, that would be like the ground state. So if m equals 1, that's your ground state. N is going to be like a second higher value, okay? They didn't know it, but later on they figured out, oh, those are your potential like energy states. So if m equals 1, for example, n is going to be m plus 1. So if m equals 1, then n can be 2, 3, 4. If m equals 2, n could be 3, 4, 5. Okay? So your n values start at one value bigger than your m. The 91.1, that's where the trial and error came through. They literally said, what number can we put on top? 91.1. They worked it out and said, okay, this is going to work. So this was literally trial and error. So they looked at the spectral lines of hydrogen and said, what can we do? So if you wanted to calculate a wavelength on an emission spectrum, for example, you would take 91.1, and then if you let m equal 1, so that would be 1 over 1, and then let's say the next value up, n would equal 2, okay? So, but that's going to get squared, okay? So, if you take 91.1 and then take 1 minus a fourth and then divide that, you're going to get a certain wavelength. Randomly, that matches the wavelength in that first spectral line. If you go to the next one, you have 1 minus 3. Now, here's the story. As if you let m remain at 1, as n gets bigger and bigger and bigger, what's this value going to approach? 0. Okay, it's going to approach 0. So basically, you're going to approach 91.1. If you go like infinitely far, basically you'll get 91.1. So on this Balmer series, mainly because of the fact that it was like the quintessential kind of we're going to know what's going to happen. This equation works. We have no idea why it works, but it works. Okay, because at the time they didn't know anything about quantum states. Schrodinger hadn't done his work, anything like that. So, but it worked. They just didn't know why it worked. And so this is why, just again, on the test, I'm never going to expect you to do this. There was a simple problem on the assignment, just so you can get an idea of how it works. So if you ever see this later on, you go, oh yeah, we talked about the Balmer series. Okay? But in terms of like, am I going to expect you to know it in great depth? No, but it's just a simple idea so that you have that. Okay. I'm done. So this is out of chapter 29. So this is the second to the last assignment I will ever give you. And yes, this is all it took. Okay?
1 page, 5.
Wait, it's a
So
page and a half, guys, I don't know.
no, and most of this is like writing big chemical symbols. So
Are we having to do that?
yeah.
What? I hope I'm hearing you guys.
Turn that phone in.
No idea
I think
why
in
it
Chem
works.
1,
It just
like
does.
over a year ago. You didn't take it.
That's science.
Time
That-
for it now, right?
100%.
I don't know why.
I'm sorry, no idea why it works, but it does. That's just science for me. That's fine.
There's something that
No.
The math works out. We don't know why the math works, but it does. I just
Made 5 different questions.
Yeah, it's better for my mental health not to.
This will make sense when you get to problem number 4. When you get to problem number 4, you have to list out the number of electrons, protons, and neutrons. Do not write random numbers and expect I know what they're going to be. What I would suggest on number 4 is that maybe you make a chart like this, where you go, here's the number of electrons, here's the number of protons, here's the number of neutrons. That'll make sense when you get to that problem. It's gonna make it easier for me to grade. You randomly writing down 3, 4, 2 means nothing, okay?
I will be doing that.
Yeah, so a chart would be nice on problem number 4.
Actually, I'm gonna put them all in.
I mean, it'd be nice, I mean.
At this point, I really just, Berg warns me not to do things and I don't end up doing it. Like, he's told me probably 5 times to square things and
And you don't.
we had one test, literally every question I missed, it was because I just didn't square the product. Every
And I
question.
tried to tell you.
You told us before, you're like, you guys are gonna forget this.
And you said
I will forget it.
you won't, and I said,
Kevin, I did the exact same thing in planetary motion, when we had to square a bunch of the distances, and I did not.
It just
Wrong
did not.
what?
The planetary motion.
Yeah.
I always forgot to square. Always.
I tried to tell you.